Good afternoon, everybody. I'm Aveek, work as part of the solution architecture group in MongoDB. Me and my team, we're based out of Bangalore in India itself. So as part of today's session, what we'll cover is how companies across the globe are using MongoDB to not just scale but build modern infrastructures, right, to cater to the kind of workloads, kind of use cases that we are seeing today in the market, right? So before I start, how many of you have actually worked on MongoDB? Okay, 2, 3, awesome, good. 4 people, okay, good. All right, let's. So what we'll do today is we'll talk about the different aspects of MongoDB, right? We'll talk about what's MongoDB as an organization, where do we stand, what do we do, what's the data model, what's the query model, right? How does it actually work, and some of the key architectural concepts, right? How does it actually work from a high availability standpoint? How does it work from a scalability standpoint, and the different deployment architectures, right? That actually makes sense. All right. So that's the latest list, November 2014, of all the database companies that are there worldwide, and a ranking of it, right? DB Engines has done a ranking of all the top database companies in the world. Surprise, surprise, if you look at it, in the top 8, you just have one non-relational database, so to speak, and that's MongoDB, right? And obviously, if you look at the numbers at the bottom, for 400 employees worldwide, close to 400 employees worldwide, 1,000 odd customers, paying customers that is, that's something phenomenal, right? To do that kind of numbers. And then you're talking about tier 1 investments from all the top tier 1 companies in the world, right? I mean, investors in the world. Obviously, MongoDB is making a big mark in the database industry. We'll talk about how and why, the following slides. But essentially, what I would like to leave with you for this particular slide is that that's the only non-relational database in the top 8, and we're actually progressing very, very rapidly up there to number 4 as well. All right, these are the use cases some of the top use cases that we have worked across the globe, right? Look at those industries out there. We're talking about mobility, talking about the Internet of Things, right? Talking about personalization use cases, things such as single view. And some of the customers out there are pretty well-known brands, people using them right now on their production environments, and it making a big difference in their actual environments, right? And we'll talk about some of the key examples in the next slide, but really, if you look at the next one, right? For example, MetLife. So MetLife is obviously a global insurance company, and one of the key challenges in the insurance industry is that you have a lot of different insurance schemes, right? You have a medical insurance, you have a vehicular insurance, or home insurance, auto insurance. Each of those insurance policies have their own schema, right? If you store it in a database, for example, you'll have completely different fields out there. So if you want to bring it together and sort of make a single view of the customer kind of a situation, then what's the biggest challenge with that? Anybody? What's the biggest challenge with when you have multiple schema types involved? Any guesses? What's that? It's okay, you can take a guess. Well, sort of comparative is probably it's a simplistic word, but yeah, you're right. I mean, many ways what's going to happen is because you have so many different data types and fields involved, how do you bring that all together, right? It's a big challenge to bring it all together when you have predefined schemas, and how do you make sense out of it, right? So what MongoDB provides is something called a dynamic schema, and we'll talk about it in subsequent slides. But essentially, you don't have to worry about predefining DDLs, making sure this is how it should look, and then make sure that it conforms to it. And when you bring data from 70 odd, 80 odd systems, to bring it all together becomes a challenge, right? In MongoDB, because you have something called a dynamic schema, you don't have to worry about it at all. Right? It works seamlessly. You can just take the data, dump it from 70 odd systems, and then make sense out of it. And how does it help for a customer like MetLife? They can get their CSRs, right, to understand their customers better. So if you call the CSR and say, hey, I've got this insurance policy with you, he can check up and say, okay, you've also got home insurance and life insurance. Can I upsell or cross-sell something to you? So it makes huge business sense. And they tried to do it initially with a relational database, and they thoroughly failed because of the cost involved, time involved. And then they did it with MongoDB, huge improvements in terms of cost, and obviously, fraction of the cost, and the time also was really, really low. So one of the really strong use cases where it's actually being used right now, it's called a single view. It could be customers, it could be products, any which way, right? I mean, it's going to work anyway. The next use case, Guardian, again, a huge media house in Europe. So one of the things that's happening in the derp world is that the newspapers that we know of is not, I mean, you don't have paper newspapers that are selling as much as, say, in India it is, right? So it becomes very critical for them to have an online portal which makes sense to the users, right? So you got to understand your users really, really well. Comes back to the same point, right? And how do you do that in a world such as, in a developed world such as Europe, right? Is to be able to very quickly innovate and see what makes sense. If you have election 2014, for example, in India, how do you introduce a portal link or a page which makes sense to people? So ability to test out something very quickly. And that's something which MongoDB provides very, very natively as well. In a relational database, for you to build something, it probably takes you 6 months to 8 months. And then to test it out and again make changes, it takes another 6 months. So by that time, your competition would have won over. It's another one where it really, really works. The agility that MongoDB provides was one of the selling points out here. And lastly, Foursquare. How many of you use Foursquare out here? I use. Okay, 3 or 4, 5 people. So Foursquare you use to do check-ins, to check out, to say I'm at this conference right now, OSI conference. It's making sense. It's a great place to be in, or what have you, right? So what happens is if I have 1 million users across the globe, right, all of them doing check-ins together, what happens to the working set? What happens to the working set? It's huge amounts of working set which has to be in memory, right? So and if your memory capacities, it increases the memory capacity that you have, then obviously what happens to the system? Slow, right? You're right. It becomes really, really slow. So obviously you want to circumvent that problem. And how do you do that? You can't obviously do it with one single box, right? Doing it by vertically scaling has its own challenges, right? And the only way you could do that is by scaling horizontally. And we have a great concept in MongoDB called sharding, which I'll talk about, through which you can scale horizontally using commodity hardware. So in many ways, you're using the power of the collective there and making sense out of multiple boxes in many ways. So these are the key use cases. I'll get into the technology right now. We'll get into the data model, right? We'll talk about some of the key aspects of MongoDB, how does it make sense, and how does it actually work. All right, so before getting into the data model, you see the encyclopedias and newspapers out there, right? So newspapers really is a fraction of the information that you have in the World Wide Web, right? And what's the information that's generated yesterday? A fraction of it is actually published in the newspaper, right? Why do you think that's the case? Relevance is one thing. Then obviously storage caps, right? 15, 16, 18 pages, right? But again, having said that, Times of India has 50 odd pages of all kinds of stuff. But anyway, regardless, there is limitations to what you can or cannot show in a newspaper because of storage capacities, right? Likewise with an encyclopedia, there is limitations to that. And in many ways, it reflects what happened in the IT industry back in the 70s and 80s. Right? Back in the 70s and 80s, hardware was extremely expensive. Storage was expensive, right? So you've got to make sure that you don't have redundancies in data. You don't have duplicacy in data. You got to make sure whatever you store is optimized. And remember, the relational databases which have been working so great over the years, they were built at a time when storage was expensive. So what does it cater to? You don't have duplicacy of data. So they make sure that they optimize that part of the storage. Right? So now there's been a paradigm shift, and we'll talk about that in the next slide. Look at what's happening right now. Most of you would have used some kind of a cloud service in what you're working on, right? So storage capacities and really the cost has gone down significantly over the years. 0.15 cents per gigabyte is like really, really cheap, right? And that's something that you could do with any of these cloud providers, right? It provides you with unlimited storage. So what happens, right? The bottom line is storage becomes cheap, exactly. So from an extremely costly storage to a cheap storage. So that changes the game a little bit. The game that we understood in the 70s and 80s is no more the game that we're playing today. There's no OPEX, right? Obviously, CAPEX rather. So we're moving from a completely different model. You don't have to initially invest huge amounts of money in licensing all kinds of databases and softwares that's there, right? It changes the entire game. And look at it. In the past, right, what we had to do was sort of, before we take the, as I talked about in the encyclopedia, you actually filter down all the information that's available and then store it because of storage capacities, right? I mean, you've got to make sure that you have a filtered down version of the data and then store it in a database. Now what's happening is we're moving towards a store, filter, distribute model. And how does it make sense? Because I have unlimited storage in some sense, right? So I can bring all the information that I want into my storage and then make sense out of it. If you think of it, right, today's problems may not be relevant tomorrow, right? For a customer or any of you guys who are customers right now, your problems today might be completely different tomorrow. The kinds of use cases that you have with the data that you have might be different tomorrow, right? So you don't know what's your problem actually in many ways. So if you have all the data that's available, it helps you make those choices at that point of time versus already having a filtered down version of data and then trying to make sense out of it. It doesn't make sense that way, right? So that's where we're moving towards. The industry is moving towards store, filter, and distribute. All right. So with that as a background, this is the database landscape in many ways. How do they all stack up, right? Where do they stand, right? We talked about relational databases, obviously. They've had 40 years to innovate, and really in terms of functionality, no brainer, right? I mean, absolutely, I mean, they have all kinds of functionality that they've had 40 years of lead time to develop, and obviously very, very large and huge in terms of functionality. But where do they actually struggle or suffer to a large extent? Where do they suffer when it comes to relational databases? Scaling out, performance, right? You can't scale up, the performance goes down because of the fact that you have joins. you can't scale out beyond a point, right? So there is limitations to what you could do with the relational data. How do they store the data, for example? That's a big challenge in itself, right? So that's the, so the x-axis is actually about depth of functionality and the y-axis is about scalability and performance, right? If you look at the other side, key value stores, extremely fast, right? Extremely performant. You query based on a key and you get the data. But there's only so much you could do. You cannot do aggregation. You cannot do rich queries that you can get otherwise in a relational database, for example. And somewhere in between is where MongoDB stands. And we want to do it as best of both worlds, right? We have a huge amount of functionality. We get aggregation. You get all kinds of indexing that you could do, rich queries. At the same time, you get performance. And we'll talk about how and all that in subsequent slides. All right, look at this data model, right? A relational database. Most of you would have used this. May not be visible at the back. Pardon me for that. But essentially, what is there is there's a person table and there's a car table. Okay, so what do you have in a person car table? A person who has many cars. So how do you join those kind of tables using foreign key, right? You have a foreign key which links the two, right? So what happens in the database? We have thousands and thousands of tables in a real life production situation. Is that when you want to do a query or an insert, you have to have multiple seeks. Multiple seeks that have to happen, right? You have to seek, because this disk which is spinning, and if you have a typical magnetic disk, the spindle has to move from one place to another place. It's very costly, right? So obviously performance goes down automatically there. And how do we circumvent that problem in MongoDB? We use something called a document model, right? And a document model, we'll come to that in a minute, but document is not a PDF or a Word document, okay? Document essentially is similar to XML, right? Hierarchical data, which has all kinds of relationships, right? Enriched data. You talk about array types, subdocuments. All that can be stored in MongoDB, right? You obviously have key value data as well. You can see name, first name, information about the person, and information about the cars he owns. And what's significant out here is that you have car information in an array because he has multiple cars that he owns, right? All stored within a document. So what's the advantage? If I query for whatever that guy's name is, Paul Miller, I get all the information pertaining to Paul Miller in one single IO seek, disk seek. So what does it mean in terms of performance? Yeah, it goes up, right? Because in one single seek, you get all the information that you need. So this is one of the key aspects of MongoDB from a storage and performance standpoint, right? We'll take this as a starting point into what MongoDB is all about. All right, so talking about the data model, right, in terms of how we store, what's a document? I talked about the fact that we support all kinds of enriched data. We support the native types, the string, int, all the basic types that are typically supported. But apart from that, you support arrays, we support subdocuments. So information that can enrich the data about something, right, about some entity, can all be stored locally, embedded within. And some of you DBAs might have a question. Okay, so this is going to mean that there's a lot of repetitive data. Information about Bentley, 1973, $100,000, right? That's going to be stored in multiple places, isn't it? I mean, if you have somebody else who owns the same car, the same information is going to be stored there as well. But does it matter anymore? Does it matter? Why? Storage is cheap. And that's very, very important to understand, right? It doesn't matter. And honestly, what we're losing out is we're gaining in terms of performance. We're going to store it in multiple places, yes, but you get all the information for this guy Paul Miller in one single seek. As well as the fact that you can do a lot of cool stuff. Look at this location information. Natively, we support geospatial information, which means that I can index geospatial information. I can have a query which actually finds out what's the closest point to where I am right now. What's the restaurant which is really close by, where can I go? Right? It helps you. I mean, most of the use cases we are seeing today in the market is all related to location, right? Where are you right now? Targeted marketing. All that is location information. So natively, from a database standpoint, can I take the questions at the very end? Just interested. I'm sorry. So natively, what we do is we support geospatial indexing, which means that you can find information closest to where you are. So every one of these fields that you see out there can be indexed. Every one of those fields, including fields which are inside a subdocument, which means that you can index them. You can actually make it really, really fast in terms of the applications you're building. So at the very beginning, you got to make sure that you understand the use case itself. All right, the data model gives you agility and flexibility. I talked about those aspects. I talked about the fact that it's naturally, it really ties down to if you look at an object-oriented language, you obviously have data which is stored in a particular way. And in many ways, the document model reflects that. You can natively store that information in a document database such as MongoDB versus having to convert it, make changes to it, build an ORM model, and then store it in a relational database. I'll not go to the third point, but I'll come to it in a minute. The query model, I talked about the fact that it gives you aggregation, geospatial indexing. You can do text search. You can find out, you can stem the data within comments, for example, and get the information. So lots of really, really advanced features. Aggregation, sum, count, group by, all that stuff that you got in the SQL world, you can do it here as well. So you get the rich queries that you typically may not get in other databases. All right, I talked about most of these things. In the interest of time, I won't talk about it in too much of detail, but just one thing. I talked about geospatial information, text search. Look at MapReduce. You have a single-threaded MapReduce. It's unlike Hadoop where you have multi-threaded. You have a single-threaded one. But if you want to find out trends, how am I selling cars over a period of time? Let's say it's a Bentley car. How is it sold over a period of time? I could do that. Run it in batch mode and find out. Right? So there are a lot of things that you could do with MongoDB. Huge number of languages that we support and frameworks as well. I mean, pretty much all of you out here would find that the languages that you're working, this is a subset of it, but we obviously support natively the drivers of all these languages, but a lot of others which are supported by the community as well. So you can just go ahead and download those drivers, and of course frameworks as well. Lots of BI tools as well. You can see some of the popular ones out there. They all have connectors to work with MongoDB, so you can use MongoDB as a store and connect to these BI tools as well. All right, scalability and availability, the key aspects of architecture of MongoDB, right? Sharding, to talk about it in a nutshell, obviously we don't have too much time, but sharding essentially is like an encyclopedia, right? Encyclopedia, you have multiple volumes of Britannia, for example, right? So what do you have there? You have a key, such as, let's say A to E, F to G. You're basically, a key is defined based on the range of values that you have, right? So that could be one way you can shard. It's called range-based sharding. And essentially, let's say I want to look up cricket. I want to see what's happening in cricket. I would obviously have to look at C. C is in volume 1, which is A to C. I would open up C and just look at that particular volume. That's exactly what we do in MongoDB. It's called sharding. So let's say I want to insert something into a particular encyclopedia, and let's say that key is of C. Let's say something called Calcutta or whatever, right? Something with C. Then what happens? All the inserts will happen in that particular volume. So we don't have to touch the other volumes, right? Exactly what happens in MongoDB as well. And if the data within that encyclopedia exceeds a particular point, you have to split it into 2 volumes. Right, so what could happen is A to CO, you could have one volume, and CP to the rest of it till D could be another volume. So you're scaling out based on the kind of data that you get in at runtime, completely seamless to the application, you're scaling out. And that's exactly what you do in MongoDB. There are a couple of other ways you could do it. There's something called hash-based tagging, so you could do like MD5, you map the key that's there to an MD5 value and then store it as well. Obviously with that kind of a thing, it's not range-based, so you can't do range-based queries, but it gives you that option. It gives you that option to store it in different ways. You can do tag-aware sharding, which means that I can say data which pertains to India should be in India alone. I don't want it to go outside India. So you create a shard for India and make sure all the data that goes there. So sharding helps you scale out. You can scale out beyond a point. The metadata is stored somewhere. The balancing happens, saying that, okay, this is way too much data in this volume. Let me split it into 2. Exactly what happens in sharding. Okay? The next one, replication. So replication, we'll go to replication. Actually, if you look at replication, it's all about high availability, right? So we talked about sharding, which is used for scalability, and replication is for high availability, which means that if one of the nodes goes down, first of all, ours is a primary secondary architecture, which means that you can write into the primary, but you cannot write into the secondary. Right? Ours is not a multi-master setup, right? The fact that we have a high availability means that we're giving you availability. At the same time, it's a completely consistent architecture, right? You don't have to lose out on consistency. You don't have to worry when you have a multi-master setup as to what data do I have, right? That's what high availability provides for you. And if somebody goes down, one of the primary nodes goes down, there's somebody else which picks up the job and does it for you. And that's called a secondary node. There are all kinds of election algorithms that we have written which make sure that the right person gets elected as a primary once one node goes down, right? So that's how it works. You look at it, there's a primary and secondary out here. So data is actually replicated using an op log, similar to Oracle's or any of these relational databases. They have these redo buffer logs or whatever logs that are sent from one node to another node. We have op log entries which are shared from one node to another node. Each of the nodes store a local copy of that data, and they apply the operations individually on them, right? They can't take write requests, but you could potentially do read requests on them, right? So you can use it as a high availability environment. It also helps you for DR. I'll just take the questions at the very end. Sorry guys, just in the interest of time. DR is actually, you can use one of the nodes which is down. We can use it to use one of the nodes which is up to bring up the node which is down, right? So you can make it completely, absolutely highly available. Maintenance, if you have to do a patch upgrade, in a typical relational world, you have to bring down the system. Here you can do rolling upgrades, which means that you bring one down, upgrade it, and bring another guy down and upgrade it as well. So you can do that without any downtime at all. All right, so let's move on to the next part of it, data architectures. If you look at the deployment architectures, a single data center, right? You have multiple racks, and obviously I'm talking about a real life example here, right? You have multiple racks in a single data center and multiple servers. There's a lot of upside to it, right? If the rack goes down, server goes down, you still have high availability. Somebody else picks it up. If the data center goes down, you're done, right? So this is obviously not a great architecture. The other one is to have a multi-data center architecture, right? Where you have nodes in the primary, in the primary data center, and also in another, let's say it's west and east, you have nodes out there, and also in central as well. I'll not talk about arbiter, but you can just assume that there's a node which actually doesn't store data, but just votes to find out who's the primary. It's a low-cost kind of a node, okay? In the interest of time, I won't talk about it, but essentially, you can create an active data center by having a secondary along with your primary in the primary data center, right? So the primary goes down, the secondary in the primary data center picks up the job and does the job for you. If that data center goes down, who picks up the job? The other data center, right? You still have nodes out there. And ours is a majority-hungry architecture, which means that you should have majority number of nodes up and running for it to work. So if there are 3 nodes, if one guy goes down, you still have 2, which is majority, and it works. 5 nodes, 3 need to be up and running. So in this architecture, if you look at it, you have 5 nodes for A, 5 nodes for B, and 5 nodes for C. If any of the data centers goes down, it still works. All right, I won't spend too much time on this, but you can also create a read global and write local architecture as well. So we have another thing called MMS, which is actually our, it's called it's basically a monitoring management kind of a service. It's called MongoDB's management service, and you can use it for creating backups, point-in-time recovery, right? You can use it for monitoring the overall deployments that you have. You can use it for automation. You can actually automate your entire deployment. You can add nodes, remove nodes in a shard, right? All that you could do on a cloud service that we provide called MMS. Okay, it could be on a laptop, for example. You could still monitor something on your laptop using MMS that we have on a cloud. Okay, it's very, very powerful architecture that we have with MMS as well, and it's helping customers use it in real time as well. So as I said, right, you have an agent which sits in each of these places, in the laptop or data center or cloud, and it monitors them. All right, so security. You get enterprise level security in authorization, you get authentication, encryption, auditing at enterprise level. And how do we provide that? By default, right, in the community version, obviously as an open source company, so you can download the overall kit and play with it. By default, you get in-database authentication X509 certificates as well, right? You can use simple tokens, for example. But if you go to the enterprise version, you get LDAP and Kerberos, authentication as well. Then from an authorization standpoint, you can do stuff such as roles, right? Obvious stuff that you do with authorization. And also redaction. You can say that this guy can access these fields, but you can't access these fields, right? All the kind of cool stuff that you typically can do. Auditing, with the enterprise version, you get admin operations auditing, and you can go for partner solutions for things such as queries, right? If you want to audit queries. Again, encryption. The enterprise version gives you SSL encryption, right? By default, you can get that. And also, if you want to do at-rest encryption of disk, say, disk level data, you can use a partner solution for that. So you pretty much get an enterprise level security solution from MongoDB. Right, last part. In terms of, so we have a wide range of audience out here, right? We have audience, probably from startups, from multiple companies. What are those websites that I need to look at if you're not a familiar MongoDB user? So I would recommend that you go for the case studies. If you're a startup, look at presentations and look at online training. For people who are already using MongoDB, I would recommend that you go to things such as documentation. It's a fantastic documentation site, probably one of the best you can ever get. You go to docs.mongodb.org, you get pretty much everything in terms of the code that you can write in terms of how it works. And lastly, right, if you want to download this stuff, it's free, as I said. Please go ahead and download onto your laptop and start playing around with it. But any questions, please do write to info@mongodb.com. I have my card, I have my colleagues' cards as well. Please pick it up. And if you have any queries about any of the deployments, any of the use cases that you have, feel free to reach out to us. Sorry, guys. Any questions, guys? You had a question. Sorry, please. I think you had a question first. Sorry. Okay, you fine? Okay.
Yeah. So let's assume that I have a product which is using MySQL as a database.
Sure.
Or DBMS.
Sure.
In production system, what kind of signal it should prompt me to think about any NoSQL data store like MongoDB.
Sure, that's a good question. His question is, he has MySQL right now, one of the relational databases. What's the signal for him to go towards MongoDB? And the answer is, if I'm scaling out, if I have an issue where, if it's scaling out beyond, if you look at growth over the next 5 years, it's growing beyond what the current capacity of a single system can provide. That's the point when you should say, okay, should I move beyond what I have? That's one example. The other one is where performance becomes an issue. If performance is a huge issue, let's say your use case is extremely performance driven. You have a user sitting out there, he's running a query to book a Indian Airlines flight, for example. He wants a response in real time, right? He wants an immediate response. I can't wait for 10 minutes for a response to come from some kind of a portal that I'm booking something in real time. Online applications, if performance becomes a key thing, that's a great example to move towards MongoDB. So performance, scalability, if you want something like a dynamic model, if you want to bring everything together, data mart kind of a thing, where you want to make sense out of your customers, want to sell them more, upsell, cross-sell, that's a great fit for MongoDB as well. So just about everything. I can talk about geospatial information. You want to natively support what's the closest point to where you are right now. You obviously can't do that natively by a relational database. You have to do a lot of kinds of, you have to make all kinds of changes to it to be able to make sense out of it. That's a great case for MongoDB, right? And if you compare to a lot of other databases, you get secondary indexes. You can make it really fast by indexing other information as well. So document model, right, if you look at it from a holistic perspective, important to remember, guys, it gives you all the kinds of facilities that you get with a relational database, but something more as well. So good question. Any other questions, guys?
I have some more
Sure.
question on that.
Can you just pass it on so we come back to you so everybody gets a chance to ask? How much time do we have for the questions, by the way? You have time? Okay, please go ahead. Yeah.
Yeah, so MySQL also, it supports scalability via sharding.
Sure.
I can shard and scale
Sure.
it, make it scale.
Sure.
And another thing is, MySQL also supports, geospatial support is there. Performance-wise also, I think, it should be okay. Other than that, if I'm
Okay. Let me ask you a question. When it comes to sharding, I mean, you can use any word that you want, right? It's essentially partitioning. What you're doing is you're not actually partitioning beyond one system. If you look at it, right, what we are doing is, I talked about Britannia volumes. Just try to think of that, right? What am I doing in the Britannia volumes? Each volume caters to some amount of data. You're partitioning data based on volumes. So you're using multiple systems to partition data. So essentially, you're doing more than what the traditional partitioning is all about. And why is that a challenge in a relational database? Can you tell me why? Why is that a challenge to scale beyond one system in a relational database? Whatever be the data, I don't want to name a single database, but any of the relational databases, there's a point beyond which you cannot scale. And can you tell me why that's the case? But why is that an issue in terms of consistency? Join, right? You have joins, so you have to bring in data from across tables. How do you do that when data resides across multiple systems? It becomes progressively slower and difficult to manage, extremely difficult to manage. You're right, I mean, partitioning is supported by a lot of databases, but they don't provide partitioning that I'm talking about, which is about partitioning data across systems. I'm going to have some amount of data which resides in one system, and the question would be, if it resides in that system, what happens to the data if it goes down? And I talked about high availability through replication. So you get consistency, right? Somebody talked about consistency. You get consistency, at the same time you get availability as well. If I look at the CAP theorem, we provide for CA as well, apart from P, obviously, right? I hope it answers your question, right? Yeah. Any other questions, guys? You had a question, sorry, please.
Yeah, one of them was sharding, so that led to my question.
Okay.
That's good. The other thing you said was there was an assumption to which I partially agree completely.
Yeah.
That storage is cheap.
Sure.
So you can have same information at
Yeah.
different places. The example was the car.
Sure.
Right? So you have same information at two different places. How do you maintain consistency?
In terms of MongoDB? Sure. So same information is maintained two places when it comes to replicated environments alone, when it comes to high availability. How do I maintain consistency? There are two ways, right? One is the fact that if the node goes down, what happens is, as soon as you write data to a primary, for example, it gets replicated. Right? And obviously, it's an offline process, but it gets replicated onto the secondaries. If I keep those servers close to where my server, the primary is, then what happens? Near real-time replication, because you're in the same data center, for example. You have almost like an active kind of a setup. Obviously, there will be a lag. I understand where you're coming from. If I set up something on the west coast and you have the secondary on the east coast, what happens? There's going to be network lag, right? Huge amounts of network lag. You will have performance degradation there. You're right. I mean, there is a downside to it. But remember, this is something which you get over and above what a single server can provide. So it's completely different from sharding. Sharding is for scale out, but when it comes to availability and replication, it's a replicated environment. So within a particular shard, I can have n number of nodes. And I can make it really, real time, because I can have those nodes within one data center, and you will have near real time replication that happens there. So you will never lose data. And there's a way in which, I didn't talk about that aspect, but there's a way in which you can make sure that any data you write into the primary is never lost. You can make sure data is written into the primary goes into the secondary as well. There's something called a write concern. If you set a higher write concern, you can make sure data is replicated with another node before which you progress as a thread or a process which is running out there.
So obviously, if I want to have complete consistency, then I will lose some of performance. Fine.
Exactly.
But then I really want to guarantee consistency. Is that possible?
Yeah, you can guarantee consistency. You can absolutely guarantee. In fact, we are a very, very strongly consistent environment by default. The thing is a trade-off, right? As you said, you actually answered my question. If you go for a consistent environment, highly consistent environment, what's going to happen? Performance is going to go down, right? You're going to have that. You're going to set a higher write concern. What is write concern after all, right? You're going to say, I'm sending something to this guy. They said these three guys are a part of a replica set, right? I tell him I sent the information to him, and from him he's replicating to the other two guys. What's going to happen there? I'm waiting for the thread to actually pass the information to the other guys before which I go to the next operation. So when there's a wait, when there's some kind of a, by default, if I don't wait for him, I just send a request to him and just go on to my next operation that I have to do, it becomes really quick. But if I'm waiting for him to replicate across the two nodes, obviously it's going to become slow. So the point is, write concern in MongoDB can be done at an operation level. I can say, hey, there's a credit card operation which is there, very important for me, for my customer, so I'll make this with the highest write concern. Obviously performance will be slower, but hey, how do we care, right? When it comes to credit card information, it's important for it to be consistent.
Highest right concern ensure 100% guarantee
Absolutely, absolutely. So it's a trade-off. You obviously don't want to use it for every operation.
The point
Yeah.
is that the database is a very sticky product, right?
Yeah.
So once I choose MongoDB and I go on with it, but at one point of time I think, oh no, consistency now for me now is a big problem. So I don't care as the performance because I have sharding, I have availability and all this stuff. But then now I want consistency.
Yeah.
So can I have 100% guarantee of consistency?
Yeah, that's what I said, right? I mean, you can get 100% consistent depending on. See, again, the point is this, right? I mean, you get pretty much everything that you want. It's a question of trade-off. You got to architect a solution. Do I want a completely? I can also read from a secondary. Mind you, if you have an architecture where you don't care about one particular transaction, I can read from a secondary and make it, eventually consistent as opposed to a strongly consistent environment. Yeah, you could do that.
And the other question was about write throughput. So you said that you have a primary
Sure.
where I can shard
Yeah.
and you have a secondary.
Correct.
Multiple secondaries where
Correct.
you can shard it.
Correct.
Doesn't write become a bottleneck? My application is very popular, it's going on.
Good question. And that's exactly what I talked about when it comes to sharding. Sharding helps me to scale out. So what happens is you can have multiple threads hitting multiple shards. Okay? It's like, essentially what happens, right? Let's say this is one shard, that's another shard, right? So I can have multiple threads in parallel talking to each of these shards. And that gives you right performance, right? I mean, the whole point is, if I have a single machine, which is exactly coming back to the same relational argument, right? If I have a single machine, have one thread or multiple threads hitting the same machine, at some point it's going to break. Right? Here what I'm doing is using the power of the collective. I'm using the power of multiple commodity hardware to do the job of what one server would do in a relational world. And that's exactly what it is about scalability. You actually answered the question itself.
No, but then the relational model has sharding as well.
Yeah, sharding again, as I said, right, sharding is within a server. It's not that you're going to be doing across servers. It becomes difficult, progressively difficult. If you have 25 nodes, if you have 25 different shards, right, and you have data across them, what happens to joins then? And join is a fundamental thing in relational data. I talked about it, right? Storage becomes, the reason it's very expensive means that you have to have joins. And what happens with more nodes being added and you partition more and more, what happens to the performance? It goes down to an extent where you can't even, we have seen it in real life, right? All of us would have seen it in some kind of production deployment. Which is why the use cases I talked about in the beginning, right? This is where you're seeing where MongoDB is really doing a great job is because of performance there. In that particular example, it's about performance. It's about scalability. Can you scale beyond a point? You can't. Because you're depending on one server's RAM, processing power, as opposed to collective. And that's where, guys, it's not just about Mongo. The entire ecosystem, right, is changing today. It's changing towards the power of the collective, distributed computing. Why is it becoming so relevant today? It's precisely because of this. Any other questions? You had a question, sorry.
Hello. If I do have to migrate from, let's say, MySQL to MongoDB,
Sure.
and I have large amounts of data,
Sure.
so is there any automated way of doing it so that I don't have to put much effort?
Sure. So first of all, it looks like in the previous session was MySQL, so a lot of questions about MySQL, but that's fine. So MySQL migration is possible. Definitely, we have a lot of use cases where customers have migrated from MySQL onto MongoDB, right? So by default, do you have a connector or an adapter to do that? No, obviously you have to implement that. You'll have to, there are a lot of partner solutions available for you to migrate from any relational database onto MongoDB. In fact, a lot of deployments, as I said, that examples I didn't show, but there are a lot of examples where people are migrating from not just MySQL, but a lot of other relational databases as well. Right? So by default, you don't get it's not part of the product that you get something where you can migrate seamlessly, but you get a lot of partner solutions that can help you do that very, very seamlessly actually. Sure. Go ahead, sorry. Yeah, there is no concept of joins at all in MongoDB. There's absolutely no concept of joins. And I talked about joins, right? The downside of joins is performance. So what you get by storing everything together, you lose out on you have duplicate data, yes, but you get performance. You get significant performance because, and that's a natural way of storing. If you look at, just think of it, right? You have something about a person and his cars. Naturally, what do you want? In one query, I want all the information pertaining to that particular operation. You want everything related to that person to come to me at one shot, as opposed to having multiple I/O requests to get that information from multiple tables and then making sense out of it.
What about the reverse of the query?
Sure.
One person owning multiple cars, you are storing one document.
Sure.
What about one car who are all owning?
Great point, great point. So that's where our rich query model comes into the picture. Right? If you saw the example, I didn't talk about it, but if you saw the example out there, you can query about on any one of those fields out there. So I can say, give me all the people who own this particular car. In one single query, I can get all that. Right? But again, having said that, your question is there a performance hit there? There will be some amount of performance hit. And if I don't index it, for example, there will be a performance hit. If I index it, I can go to that specific document, get the data. Right? There's many ways in which you can model that. One is I can keep it the way I modeled there, and then write a rich query to get me the data. If I want even more performance, I can reverse the collection. I can have the information about the car and the people who own it. So there are many ways in which you can model it. It depends on what problem you're trying to solve.
Depends on the problem. And
Yeah, exactly. So this is one thing which I want to take away, guys. In MongoDB, you need to understand the use case really, really well, right? Unlike in traditional databases where you build a logical model, physical model, and then sort of say this is what I conform to. Now make sure that you fit everything into this, right? Here it's not like that. Here is this is my use case. Now let's see what we can do. I'm going to change my use case tomorrow. That's fine. MongoDB provides that for you. So ability to change, scale, agility is something which you don't get in any of the other databases that you can think of. Please.
Change of use case will not be working very well, right? Because once you have accumulated data over years
Sure.
or something.
Sure.
Now tomorrow you say, okay, now I also want to query and
Perfect.
additional data I want to collect.
Sure.
And retrospectively add it to previous record.
Okay.
That kind of thing will be very difficult.
So actually, very good question, but I'll probably answer it. In fact, you're exactly hitting the point where relational databases don't work well. So in MongoDB, it doesn't matter. Let's say you had the car model, right? You had the car data model that you had car and people, right? Let's say tomorrow you decide, oh, okay, car, I want to have information about the color, I want information about its height, its weight, its width, whatever. You can add that, at any point of time. Now, talking about data which you have to, retrospectively change, that's a relational world question. Because in relational world, you have to conform to something. You have to conform to some kind of a data model. There has to be a column which has to be added, and you have to make sure you take a decision about what you do with those columns, with the previous billions of records that you have. In MongoDB, we don't care. I'll say, okay, if I don't want color, I'm not going to do anything with the old records. I'll just leave it as is. So any question that comes in tomorrow with just color, we'll hit the records which have color information. If you want to go ahead and change it, go ahead and change it. So that's something which you don't get. You have to make sure that you take that choice in terms of a relational database. You have to make sure that you think about what you do with the old records. Here you don't have to do it. There is an option that you have. You can make those changes or you can keep it as is and write queries to get the information. Sorry, you had a question. Did it answer your question first of all?
Can we take the questions offline? Because it's almost...
Okay, last question, sorry. Please, go ahead.
In case of audit members, I would have put the cards in a separate table.
Sure.
And each table has just a pointer.
Perfect. Perfect.
So if something extra I had to do for the card, I would have opted only that single table.
Perfect.
Right. But here, if I want to update, I have to update all the records.
So that's an extremely good point, right? He says if I have a car in a relational database, I have a car table, I keep it outside, then the advantage is if I update it, I can update it in one place, right? It's a very good point. In fact, if you have data which is very, very frequently changing, let's say I have people and car inside. It's an example, by the way. Let's say you have people and car inside which changes very, very frequently. The point is, then what you have to do is you obviously have to change multiple, update has to happen in multiple places, right? That's when you need to question your data model. You say, okay, should I have car within people? I should have probably had it outside. So what I'm saying is you can do it that way as well. You can reference the information. I can reference it outside, keep the car information outside as well. But there's a loss there. The loss is in that you have to fetch a couple of times. There's IO seek that happens in two places as opposed to one. You can implement it that way as well. The thing is you need to understand your use case. If your use case is about updates very frequently, keep it outside. But if it's most cases you don't have to update things. If it's a car information, it may not change that frequently. If it's one-off updates, don't worry, embed it and change when required. And the update model is very, very, very powerful in MongoDB. You can update all the documents at one shot. You don't have to worry about it. So if you have to do it, you can do it. But again, the point is, architect it properly. At the very beginning, think of what's the business case, understand it properly, and this is the best model to start with. No, joins are not supported. So okay, coming back to the referencing part, right? So referencing part, there's no constraint check. So if I have a situation where there's a particular foreign key, it doesn't exist in another one, MongoDB doesn't check for it. It gives you the ability to store in multiple places and query for it. That's all. There's no constraint check. There's no join. You have to do two queries to find it. You have to fetch this information, get that ID, and search from here. It's not a join. Okay, there are two separate IO requests that have to happen. That's just the thing that you can use if required. By default, I would recommend that you use embedding. You embed all information that's required for an entity, unless until that data is going to change very, very frequently. Right? No, SQL is not supported. But what we provide is as powerful as SQL. I talked about the fact that in terms of functionality after the relational world, ours is the next in terms of that, right? That's because our query language is very, very powerful. You can do all kinds of aggregation, map reduce, things that is required in today's world. So we don't support SQL natively, but you get all these kinds of stuff.
More it's suitable for data, which is more not changing too much, too frequently.
No. In fact, it's suitable for data which changes very, very exactly opposite. Right? It's suitable for data which changes very, very frequently. In fact, in relational world, if data changes very, very frequently, it becomes a huge issue. See, just imagine alter table, adding a table, making those changes in the entity model, then linking them together, making those choices in terms of data, as he said, right? What do you do with the existing data? All that becomes a problem in relational world. In MongoDB, I don't care. Sure. Sure.
Talking about the data per se.
Yeah.
Like you have a historic data which keeps like a Twitter data.
Yeah.
Right? That historic data never changes, right? It stays there.
Sure.
So it's
No. It's suitable for all kinds of data, right? If it's a Twitter table, that's perfectly fine. If I talked about MetLife, right? Don't you think that's frequently changing data? Insurance policies keep changing every other day. And the data that comes in, I might say, I need to have information about Aadhaar card in my, medical, whatever, home insurance thing. For medical, I might store something else. That's change of data. That's data which changes very, very frequently. And that's exactly where MongoDB is a great fit. And relational database actually, if you think of it, right, they're absolutely not a fit there. If data changes, if data remains static, let's say all the fields are as is, you have 2 tables, 3 tables which are predefined, nothing changes, no scalability issue, relational database might be a good fit there. But if you have a situation where things change, right, and that's probably the most common thing today, right, change based on volume, change based on type, then that's where MongoDB is an absolutely brilliant fit, right.